I'm going to take you through a NIRCam custom pipeline example. Now, if you're wanting to run this notebook live, I suggest running this run default pipeline cell right now. The reason being is that it takes about 8 minutes to run through all the pipeline stages, so you can get it running right now while I'm doing some intro material. So yeah, if you want to run along live, do this run the default pipeline cell right now. Okay, so this notebook is going to calibrate NIRCam imaging data all the way through the JWC pipeline from uncalibrated images to a combined final drizzled image. After processing with the default settings, several issues will be discovered and investigated. We'll solve each of these issues through a combination of rerunning the pipeline steps with custom pipeline settings and manually modifying the images in between pipeline stages. And along the way, we'll leverage several useful pipeline functions to help investigate and correct these issues. And then finally, at the end of the notebook, we'll compare the final products of the default pipeline run to our custom pipeline run. So to get started, go ahead and import all of the data and all of the necessary packages. Now, if you do want to make this environment by yourself offline, I put the instructions on how I did it up here. You should only have to install the JWC pipeline environment, and all of these packages are included in that default environment. After that, go ahead and import this convenience function. This is going to be useful to diagnose some up-the-ramp behaviors later. So okay, for this example, we're going to take 5 dithered full-frame detector B3 images of a sparse calibration field near the ecliptic. The data uses a readout pattern of deep 8 with 4 groups per integration. And the filter used is F070W, so the bluest filter on NIRCam. And we'll also use the 5 corresponding long wave images for source identification. So to get started, we are going to run through all 3 stages using all of the default pipeline settings. This is going to give us a baseline to see what the default pipeline gives us, and we'll use it for comparison to our custom run later. So in this cell, to start out, we take all 5 of our uncalibrated files and run each of them through the detector 1 pipeline. Now, I do tell it that during the jump step, save the results. And I also tell it to skip the dark current step. This is solely to save time. This step can take very long for NIRCam. And in the shortwave, it doesn't do too much. So we'll just go ahead and skip it here. And then what I'm telling it here is just telling it to add the _default suffix to all of the pipeline output products. This is going to help us distinguish it from the custom run later. So once that finishes running, we'll take the output of the detector 1 pipeline, which are those rate.fits files, and we'll run each of those through the image 2 pipeline. That's going to give us the cal files. And so next we'll take those cal files, wrap them up into an association, and feed that association into the image 3 pipeline. And when I run the image 3 pipeline, I tell the tweakreg step to save the catalogs. So these are the catalogs that tweakreg is using for source identification, and that's also going to be useful to diagnose some alignment issues later. So once this runs, it takes about 8 minutes in my experience. You'll have your final pipeline product. And so here's what that looks like. Now you can see that this image has several issues. Immediately obvious is that there's multiple copies of each of the sources. So this is telling you that somewhere in the pipeline there's a misalignment happening. The upper right corners of all of the 5 input images seem like they have an increased background level. There's a strong horizontal noise across the whole image. And there are also several smaller artifacts with bright halos. And let me actually bring down my DS9 window so I can zoom in and show you those better. So here's that default pipeline product. And now these kind of donut looking things here are those strange artifacts I'm talking about. There's also another weird processing artifact down here. So we'll go ahead and look into those later. And yeah, so for the remainder of this notebook, we're going to investigate and correct each of these issues and generate a new final product using some custom pipeline processing. So the first thing that's useful to do whenever you see some strange behavior in your data is to check that you are using the most recent pipeline reference files in your pipeline run. All of these reference files are stored in CRDS, which I've linked here. So what I'm doing in this cell is I'm going to take that final drizzled image. This is one that's been run through all stages of the pipeline, so it'll contain all of the reference files in its header. And so I read in the header to that file, and then I'm going to pass it into this CRDS function called getRecommendations. What this is going to return is a reference file mapping that is a dictionary of the step name and the reference file that CRDS says you should be using for that step. So then the loop here is going to go through each of those recommendations for each step, and it's going to compare that recommended reference file to the one actually used in our pipeline run, which you can get by looking in the header of the image file, and then it's going to print any mismatch that it finds. Now in our case, if you scroll down, you can see that for every step, it looks like we are using the correct one in this case. For example, for the flat step, it says we should be using this one, and that's exactly the file we used. The only strange message we got was down here, the dark reference file is not found, and that's just because we skipped the dark current step way back in that default pipeline run. Now, while I use the drizzled product here, you can run this exact same cell on the rate or cal files that are processed earlier in the pipeline. It'll work just the same. And now I will just show you real quick that if you ever do want to find these reference files to investigate them, I'll show you how you can actually find them in CRDS. So we're going to use the mask reference file as an example here. So if you want to investigate that file, you can go to the CRDS website, which I've linked here. So this is where all the reference files are stored by the pipeline. You can click on the instrument. So in our case is NIRCam. We are curious about the mask reference file, so go down to that section. This will give you a selection table of all the reference files available. In our case, we know the name, so I'll just type it into the search box. From there, you can click on the file, and then once this page loads, you'll have the option to download the file up here at the top if you actually want to see what the reference file looks like. You can also click on database, and it'll give you some information on why the file was delivered. Usually there's some improvement, or how the file was made. But in our case, everything looks good, so it looks like the issues we're seeing are probably not due to a reference file issue. Okay, so to start, we are going to try to figure out what's happening with those strange artifacts. To do that, we're going to use that convenience function we imported previously. And so what this is going to plot here is one of the examples of one of those strange artifacts in the rate image. And then these middle panels here are showing that exact same cutout in those jump.fits files. So the same region, just showing it's up the ramp behavior this time. And then the bottom shows the corresponding data quality arrays for each of those groups. So in this case, we can see that in the first three groups, not much is happening in this pixel, but then in the final group of this image, a big bright circular ball appears. So these objects are called snowballs, and I've linked some more information here. These snowballs are pretty common on NIRCam. They're bright circular sources caused by large cosmic ray impacts. The cores are often saturated, and the full extent of their impact is often missed by the jump step in the pipeline, resulting in the rate images, resulting in them being included in the rate images because they are unflagged during the ramp fit step. So you can kind of see by eye here, here's those jump flags that the pipeline flagged in the jump step, and you can see they don't really expand outwards to capture the full extent of this object. And so those fainter wings there get included when it does the ramp fit, which is why you get an elevated level in those regions in the rate image. So the pipeline itself, like Misty showed, has several parameters you can turn on that are specifically designed to work with these snowballs. I've linked the jump step arguments page here, and if you scroll down to the snowball section, they'll show you some of them. But in our custom run here, what we're going to do is tweak several of those. Basically, what it'll do is it'll identify these objects, and when it finds them, it's going to expand those jump masks outwards to make sure the full extent of these objects are captured. Now here's that other strange artifact I noted in the rate image. Now this one has a little different nature, so it looks like it's actually a moving object if you look up the ramp. So I'm guessing this is an asteroid since we are looking at the ecliptic here. But what ends up happening is similar to that snowball where that core is getting flagged as a jump, but those masks don't expand outwards enough to get the fainter halo, and so that halo ends up making it into the rate image. So that means the same solution to the snowballs is going to be used here, which is just expanding these outwards with some custom settings, and that should make sure that they disappear from the rate image. So this officially starts the custom pipeline run. This time we're going to take 5 of the uncalibrated files and run them through the detector 1 pipeline. Only this time when we run the jump step, I'm going to tell it to expand large events, which are the two I showed up there, as well as anything like them. The large events are going to be defined as any 100 interconnected pixels that are flagged as a jump. We won't require the cores to be saturated just to make sure we get some of the fainter ones. And then for those large events that are found, we're telling it to expand the jump flags outwards by 2.5 times its original size. And then similar to the default run, we're going to skip the dark current step just to save time. So if you look at the outputs of this custom run and go back to the same two objects, here's what it looks like now. So there's that first snowball we showed, and now in this case, you can see that jump flags are they're much wider, so the full extent of it's getting captured. So there's no remnant of it after the ramp fitting step in the rate image. And then similarly for that suspected asteroid, the masks are much more expanded now, so you don't get any of that bright halo showing up in the rate image. Those bright white pixels are actually NAND, so they'll be flagged by default in the pipeline. So okay, it looks like with that custom setting, we should be good to go with the snowballs and other objects. So we're going to turn our attention to the next issue. So the other thing that we noticed in that default drizzled image is that it looked like all 5 of the images had an increased background level in the upper right-hand corner. So what I'm showing here is all 5 of our input images sorted by exposure start time. Now you can see in each of them that upper right corner has an elevated level. It looks like its signal decays with time, and it's fixed in the XY location. It's not moving around with the dither pattern. And so both of these things are telling you that you are likely dealing with persistence. Persistence is a residual signal caused by bright sources to the image prior to the affected data. In our case, there was a bright main belt asteroid survey just prior to our data set, so that's probably the source of our persistence. Now, several areas on NIRCam are especially sensitive to persistence, and I put a link here showing where those regions are. So here are the persistence maps, and these are showing you which areas on each NIRCam detector are most susceptible to persistence. So the pink and white areas are especially sensitive. So let me scroll down to the detector we're dealing with, which is B3, this upper left one here. And so you can see, sure enough, that upper right-hand corner is very susceptible to persistence. So all things considered, that's probably what we're dealing with here. Now there is a persistence step in the pipeline, but it doesn't actually do anything at the moment. And persistence model is still ongoing. So what we're going to do here is we are going to manually flag these areas with high persistence in each image's data quality array before running the remaining pipeline stages. Flagging it like this is going to prevent those areas from being used when creating the final drizzled image. Now while we're flagging persistence here, this exact same method we're going to use can be used to flag any other anomalous features in your data, such as if you have some strong scattered light features like the NIRCam claws or anything of that nature. So since we are tweaking the data quality arrays, I do want to do a brief overview of exactly what they are. Previously, we imported this DQ flags from the pipeline. If you just do .pixel, it's going to give you a dictionary of all the available bad pixels, as well as their values in the data quality array that are recognized by the pipeline. So these data quality arrays are additive, so if a pixel is flagged as both dead and do not use, the value in the DQ array is going to be 1024 plus 1, so 1025. As you can see, these numbers can get very big, and oftentimes pixels are flagged as several different things. So it can be hard to tell just looking at the data quality number what it actually represents. If that's happening to you, you can use this convenience function called DQ flags to mnemonics. This function just has you import the number you're curious about, and it'll return what that number actually represents in words. So for example, if you see this number here in the DQ array, that's telling you that that pixel's flagged as these 3 different things. Now working with data quality arrays, here's just a quick example. We're going to read in the DQ array from one of the rate files and calculate the total number of dead pixels. Now when you do this, you need to make sure you use these bitwise operations. If you just go into the data quality array and look for anything flagged as the dead pixel value, which is 1024, you'll miss pixels that are flagged as both dead and something else. Those are additive. And so doing it this way, make sure that you're capturing all the dead pixels, not just those that are solely flagged as dead. And then the inverse here is just showing you how to find the number that are not dead. It's the same thing, just with a double equal sign. So we'll use this logic throughout the remainder of this section. Okay, so in our example, I have given you a pre-drawn DS9 region file called persistence.reg. So what we're going to do is we'll translate that region file into a mask with the same image dimensions as our data. We'll then flag that area as persistence and do not use in each image's DQ arrays. That do not use flag is going to make sure that the pipeline ignores those pixels during the image 3 processing. And now I'm using a DS9 region file here. You don't have to use DS9 at all, and I'll just tell you how in a second. But if you do want to draw your own region in DS9 to mask anything you want, you can follow these instructions here. Basically, you just open the image up, draw a polygon around it, which can be as detailed as you want. And then when you save the region, make sure that you set coord system to image, just to make sure it's in XY coordinates. And this whole first section here is just reading in that region file and getting a polygon object. The polygon object's printed here. It's just the XY indexes of all of the locations of our polygon that we drew. Now, if you didn't want to use DS9, right here, you could simply just say polygon equals and then list the XY indexes of the region you want to mask. No matter which way you go, the next thing is this. This is going to take that polygon and turn it actually into a 2D image, the same size as our images here, which are 2048 by 2048. And so the resulting mask is this. So that's the top right corner we're going to mask, where its values are 1 and everything else is 0. So next up, we're going to take that mask and modify the rate image data quality arrays. So to do that, we'll read in each of the rate files. We'll get the original data quality data, and we'll get ready to make a new data quality array, which at the start is just a copy of the original. And then what we're going to say is, okay, for any pixel in that persistence mask that's not already flagged as persistence, add the persistence flag to that pixel. And similarly, for anything in that persistence mask that's not already flagged as do not use, add the do not use flag to that pixel. So doing it this way is important to preserve any other existing DQ flags. For example, if you just tell it to add the do not use flag, which is 1, to all of the values in that persistence mask, if a pixel is already flagged as do not use underneath that mask, you will now call it 1 plus 1, which is 2. So it's called a saturated pixel then. So doing it this way is making sure you're only adding those flags on pixels that don't already have it. And in that way, you're preserving all of the existing information. So once we have that new DQ array, we can update the DQ data and just write out the file. So there's an example here of the original data quality array. There's our modified one, which is identical to the original, just with that region flag now. So next up, we can run the image2 pipeline with our modified rate images. Those data quality modifications and custom snowball handling above are going to be carried over by default. So no custom settings are needed here. We're just going to take each of our rate files and run them through the image2 pipeline to get our cal files. Okay, so with that solved, next we'll turn our attention to the other issue we saw in that drilled image, and that was that strong horizontal noise stretching across all of the detector pixels. So this horizontal noise is called 1/f noise. It's a correlated noise that appears as horizontal banding in NIRCam images. The reference pixel step way back in the detector 1 pipeline is designed to correct for this noise, but it isn't perfect, and remaining horizontal banding can be seen throughout the later stages of the pipeline. This is a really common issue on NIRCam, so several community tools I've linked here have been created to correct this remaining 1/f noise. In this notebook, we're going to apply a similar correction to those community tools, which is we'll subtract the source mask, median mask row values relative to the pedestal from each image. And then while we're correcting this 1/f noise, I'm also going to tweak the overall signal levels in the 4 amplifier regions to better match each other, as the borders between neighboring amplifier regions often show an abrupt change in background level. So in case you're not familiar, the NIRCam full frame is right out through 4 amplifiers, each one representing a equal sized pixel area. So for example, the rightmost 500 row pixels here are all read out through a different amplifier than the remaining detector. And as you can kind of see in this image, right at the boundary of that amplifier, you can get some abrupt drops in background levels or increases in background level. And so we're also going to correct for that effect while we're doing this 1/f correction. So before doing the correction, we need to get a source mask. Now to do the source mask, we are actually going to use the corresponding long wave images. The upper left quadrant of the B long wave detector has a very similar field of view to our shortwave detector B3, so that's why we're able to do it this way. In this case, the reason we're using the long wave is just because the sources show up much more brightly, so we'll make sure that we're really capturing the full extent of these objects in our source mask. Now, another common reason for why people use the long wave for the source masking is the short waves has a stronger impact when you're dealing with scattered light features and large scale persistence. So in the shortwave, it's oftentimes hard to get an accurate source mask beneath those features. The long wave isn't as impacted by those things, so people will use the long wave to get the source mask underneath those features in the long wave, or in the short wave. And then once you have that long wave source mask, we'll use a pipeline function that blots that back onto the shortwave pixel space to get the corresponding shortwave segmentation mask. So this cell here is just going to take each of those long wave images and it's going to make a segmentation mask. To get that, we just read in the data of the long wave file. And what we'll do is we'll smooth it with the Gaussian filter before source finding. And when we detect sources, we will flag any 8 interconnected pixels, 1 sigma above the background, which is a threshold we'll use as a source. And then I do one final smoothing on that seg map itself just to make sure we're really catching the extent of those brighter source swings. And then we just write out the segmentation map for each long wave file. So there's just one example here. There's that long wave image, and there's our corresponding source mask we just made. So now what we have to do is we have to take that source mask and blot it back onto the shortwave pixel space to get the corresponding source mask for the shortwave images. To do that, we're going to take advantage of image models. So we imported these previously, and what we'll do is we'll first read in the blong file and put it into an image model. We'll then update the data in that model to be the long wave segmentation map we just generated. Then we'll make a second image model, this time the shortwave image model. And then we feed both of those models into the pipeline JWCS blot function. So what this is going to do is it's going to blot that long wave data onto the shortwave pixel space. And that blotted data is going to be the seg map we'll use for the shortwave. So visually, just what's happening here, there's our shortwave image. On the right is the long wave segmentation mask, where I've outlined the rough field of view of the B3 detector. And then in the center there is that blotted data, and that is the data we'll use for the shortwave seg map. Now, if you do use this method, one thing to note, while the field of views are similar, they're not perfect. So you can kind of see on the left edge here, there's some missing data, maybe 20 or 30 pixels. In our case, it won't matter because we're going to do some image-wide stats and we'll do some extra sigma clipping to be safe. But if you are using this blotting method, that's just something to keep in mind. Okay, so now that we have the source mask, we can actually go ahead and run that 1/f correction. To do this, we'll read in each of those cow files. We'll get its science data, its data quality array, and that seg map we just made. And we'll make a masked version of the data where we're going to mask anything flagged as a bad pixel, which is anything where the data quality array isn't equal to 0. We'll also mask anything that's a source. And then to be safe, we'll do one final clipping on that data and add anything that got clipped onto that mask as well. So once we have that, we calculate the full frame median, as well as the median collapsed row and column values. These are going to represent that residual 1/f noise and amp offset respectively. When we do these, we make sure to do it relative to that overall median value. This is just going to make sure that we're not changing the overall levels. We're just going to correct the offsets from that overall level. And then since that column offset, the amp offsets are a larger scale effect, I do median bin those in 16 pixel bins just to denoise it a bit. 16 is chosen here, so one of the smaller bins will line up perfectly with the amplifier boundary, which is every 512 pixels. And then those collapsed row and columns are 1D arrays, so this cell here is just repeating each of those across our full 2048 by 2048 image to get the 2D correction image. And then our corrected data is just going to be the original minus that corrected image. We update the science data to be that new data and write out the file. We'll add the _core just to distinguish it from the original. Okay, so here's one example. There's the original on the left. There's that 2D correction model we made in that cell. And on the right is that new corrected data where you can see there's much less horizontal noise, as well as that amp offset getting corrected. So at this point, we have a snowball corrected, persistence flagged, 1/f noise corrected data. The only thing we'll have to do is to drizzle all of our custom files together to get a final drizzle product. However, like we saw in that default drizzle, the default pipeline run showed multiple images of individual sources. So this is suggesting that there's some issue with the alignments in the image 3 step. Since the images were misaligned, the sources themselves in some images are flagged as outliers. and only their fainter wings can be seen in the final drizzled image. This can be confirmed by inspecting the cosmic ray flagged or underscore crf.bits files data quality arrays. These files are identical to each cal file. They've just had their data quality arrays updated with any outliers found during the outlier step in image 3. So here's an example. There's a cutout of our default drizzle where you can see those multiple sources. The middle image here is a single image that went into that drizzle. This is one of the images that was misaligned. And so if you look in its corresponding CRF file, you can see that, like that bright source there got flagged as an outlier twice. Since it's misaligned in one part of the sky, it looks too high, and one part it looks too low, so that's why you'll see it flagged twice as an outlier. So if you scroll all the way back up to that default pipeline run, you can see that for a couple of the images, TweakReg actually didn't find enough sources to match on. It wants at least 10 by default, and so for those images, nothing actually happened. But there were a couple of images where TweakReg thought it found enough good sources to perform a shift on. However, those shifts were very high. And to see the shifts, if you look at the log file, it's those XSH, YSH outputs. So in our case, it shifted this image by 2 arc seconds. If you align these images in WCS space just by default, you can tell that they're already pretty well aligned to within 1 or 2 pixels. So this big of a shift is definitely unexpected. So if you get a strange shift in your data, a good thing to do is to, look at the image, and then what I'm doing here is I'm circling all of the sources from that default TweakReg catalog from the pipeline. So these are all the sources that TweakReg is going to match on or attempt to match on. And what you can see in our case is that if you look at the same cutout of the data quality array, you can see that every single pixel that TweakReg found here is actually an outlier pixel that's flagged as a jump in the data quality array. So these aren't real sources. So what ended up happening is probably TweakReg was aligning on bad pixels, and that's why we got an unexpected large shift in these images. So I just want to investigate for a bit why these pixels are showing up as outliers, and this is also going to show you how the jump step actually works. So here's one of those outlier jump pixels, and here's its up the ramp behavior. So in group 1, not much is happening. In group 2, it looks like we get a big cosmic ray hit, and the pipeline accurately flags it as a jump. Now in stage 3, there's also an increase in signal, but there's no jump flag. And then in stage 4, there's almost no accumulation of signal, but it's mysteriously flagged as a jump by the pipeline. So how this jump step works is that it's going to look at every single consecutive group difference, and then it's going to calculate the median group difference out of those values. And then it'll compare each of those individual differences to that median group difference. Now in this case, the median group difference here is actually that group 2 to 3 difference. So that's what this step is seeing as the expected jump behavior. So when the pipeline looks at that 3 to 4 jump, it actually sees an outlier. The jump step flags both high and low outliers, since that short jump is much different from that median jump group difference. And so that's why group 4 is flagged. Now, since group 3 is the typical behavior expected, the pipeline doesn't flag that group. And then the group 1 to 2 jump is big enough to where it can overcome even that high median group difference value, so the pipeline still sees it as a jump. But what you're left with here is that now the pipeline is going to fit the good groups, which it thinks is groups 1 and 3. And as you can see, just based on the plot here, that results in a very high slope value, which sure enough is what you see in the rate image, a really high rate fit. So that's the source of these strange outlier pixels in our case. And so this case here highlights one of the reasons why we do recommend to try to use at least 5 groups when you're planning your data. It's not always possible due to data access warnings, but these are some of the issues that can come up when you're using a lower number of groups. So at the moment, the pipeline can't actually fix these. So since the pipeline is locking onto these as sources, what we're going to do in this section is just make our own source catalogs, and then I'll show you how you can feed your own custom source catalog into the TweakReg step, rather than having TweakReg do the source binding for you. So you can make your custom catalogs any way you want. In my case, what I'm going to do is I'm going to do the source binding on a bad pixel smooth version of our input images, just to avoid flagging those as sources, those bad pixels. To do that, I just read in each of the data. I make a mask of all those jump pixels and do not use pixels. I get a smooth version of the data, and then I find the ratio of the original to the smooth data, and then I say for anywhere where the mask is true, so anything flagged as a jump or do not use, and anything where that ratio of the smooth to unsmooth data is greater than 100%, replace that pixel with the smooth version. So the step here is basically just going to replace those bad outlier jump pixels with a smooth version of the surrounding good pixels. And then while I'm here, I also tell it to ignore anything flagged in that persistence region, just to avoid any source finding happening in that bad area. Now for the source finding itself, I'm going to feed in that cleaned image, and I'm going to use DAO star finder, just with some basic settings. This is the same algorithm used by the pipeline. And then once I get those sources, I just write out the results in a table, the same format that the pipeline expects. So visually, just what's happening, there's a cutout of the original image. There's that bad pixel smooth version that we just ran the source finding on. So if we go back to that same cutout region, we can now see if we look at that area, these new catalogs are actually finding some good sources that aren't just bad pixels. This pixel on the left here is actually a bad pixel. It's actually a hot pixel. If you remember, we skipped the dark current step. So that's one of the results of skipping that, is you get a handful of hot pixels left in your image. But since we have plenty of good sources here, TweakReg should be fine. Okay, so now we can run the final stage of the pipeline, image 3, to combine all of our custom images into a final drizzled product. When we run this, we do need to make sure to feed those custom catalogs into the TweakReg step. So to do this, we start out just like normal, where we take all of our cal files and we wrap them up into an association. However, for this time, we're going to add a new parameter called TweakReg catalog to each member, so for each image. And the value for that TweakReg catalog is just going to be the catalog name for that image. And then we just write out that updated association like normal. So the only other thing you have to do to use those catalogs is that when you make the call to image 3, make sure that you set use custom catalogs to true in the TweakReg step. Now I do modify a couple more parameters here. We are dealing with a pretty sparse field, so I dropped the minimum objects to match down a bit, and I decrease the search radius and tolerance just to avoid it trying to match too far out, since they are pretty well aligned by default. And I'll just note here that before you do all this custom catalog stuff, a good thing to do is to just play around with the TweakReg source finding parameters. I'll put a link to those here. So you can change the sharpness, roundness to try to get the best sources possible to align on. I would definitely recommend trying to set the absolute reference catalog to Gaia DR3. That's going to match your image to a well-known catalog, which could solve your issues by default. In our case, there weren't enough Gaia sources in this field of view to get a good alignment, so we just went this custom catalog way. Okay, so now we ran the image 3 pipeline, and let's inspect the log file. So now if you scroll down in the log to the TweakReg step, you can see that now TweakReg is using a user-provided input catalog. So it's not doing any source finding by itself, it's just taking our catalogs as truth. Now if we scroll down to the first images it aligns, which is this one, we can see that it finds 20 source matches. And now the shifts that it's applying are much lower, so within a pixel, which is more like what we expected, just because default alignment is pretty good. And so this is true for the other core images as well. So it looks like those custom catalogs fix our issue here with the alignment. Now once that cell finishes running, you'll have your final custom product. So there's that custom drizzle we just made with our custom run. And for comparison, there's that default pipeline run we did way back at the start. So let me actually pull these up in DS9 so we can poke around a little bit. So yeah, there's the default one and there's our custom one. So one thing you can note immediately is our sources are aligned. There's no more misalignment. If I zoom in a little, you can see that horizontal noise is a lot decreased. Let me go over to this region, which had a lot of snowballs. You can see in that new version, they all get smoothed away. And then since we masked those upper right corners of all the input images with the persistence, they're not being used anymore in the drizzle steps, so you don't get those abrupt changes in background level. Now, of course, when you do mask a region, you lose coverage. So in the upper right corner here, we only had one image in that part of sky. And since we masked it, we're left with the hole in the image. So that's one thing to consider if you do some manual masking, is it'll be a trade-off that you just have to decide if it's worth it. And then if we check out that asteroid remnant down here, so there it is, goes away in this new mosaic as well. Now you can see there's a snowball that still snuck its way through right here. If you remember way back in the custom jump step, we used 100 interconnected pixels to define a large event. I'm guessing if you drop that down to maybe 80 or something, this one probably would have gotten picked up as well. So yeah, I think that is it. The last cells just show how some basic stats, just showing how the noise gets a little bit better in these custom images.